record. All right. So I'm going to resist the urge to do, uh-oh, what happened? Please stay on the line. It's all empty. There, it reappeared somehow. I don't know. I'm going to resist the urge to do review, and that feels really rude, but it's all in these slides, and I know that, and I still can't shake this urge to basically redo last week all over again, but we can't do that. But we did talk about resist the urge. Let me see here. I'm resisting. Let's start with an example. How about? So what's happening is chapter 5, we finished chapter 5 last day, which was introducing all these new concepts, specifically confidence intervals and hypothesis testing. Hypothesis testing is this huge can of worms where there are all those steps, right? You state your hypotheses, you do the test, you find the p-value, then you draw your conclusion based off of the p-value, right? And it was this big elaborate thing that we are going to come back to, obviously. But this is section 6.1, which is just inference for a single proportion, which is exactly what we've done. Okay, so it's just kind of laying it out again with one additional thing that we could do if we wanted to. What if we don't want to? Well, too bad. So the scenario for this example is, well, it's quite lengthy, so I'll just kind of skim through it. But 2 scientists want to know if a certain drug is effective against high blood pressure. The first scientist wants to give the drug to 1,000 people with high blood pressure and see how many of them experience lower blood pressure levels. That's a way to do it, but you can see the problem, right? How do you know if it was lowered by the drug or if it was lowered just by life, right? And so usually we need to have some sort of control group. Okay? And so the second scientist wants to give the drug to 500 people with high blood pressure and not give the drug to another 500 people with high blood pressure. So both of them are high blood pressure groups. One of them gets to the drug, one of them doesn't. And then we want to see how many in both groups experience lower blood pressure levels. Oh, sorry. So our options, so really what we're getting at is which is the better way to test this drug. Now I've already kind of led you down the route of 500 get the drug and 500 don't. Okay, so it's more a question of can you recognize good sampling? Okay. Oh, I forgot to delete the ones where they give the answers, so just scroll through that. Now the GSS, I can't remember what the GSS, the General Society Survey or something like that. I can't remember what GSS stands for, but this is just a survey. So the GSS asks the same question. And so we are looking at the distribution of the responses. So how many said all 1,000 get the drug? 99 out of 670 said that's the better way to do this. And then, of course, everyone else, 571 of them, said, well, you should probably split it up. 500 do get it and 500 don't, and then you'll be able to compare them. Okay? And so what we want to know, or what we want to estimate, is the proportion of all Americans. So now the proportion of all Americans, that's a population proportion, right? So this is a population proportion, P. So we want to estimate the proportion of all Americans who have good intuition about experimental design, which is really just, would they say that 500 should get the drug and 500 shouldn't? Okay. So it's kind of this lofty way of getting proportions, but that's okay. And we want to talk about what are the parameter of interest and the point estimate. So the parameter, remember, the parameter is from the population. Okay, so the parameter of interest, the thing that we want to draw our conclusions about and learn about, is the proportion of all Americans who have good intuition about experimental design. So P is a population proportion. The point estimate is our sample version of whatever we're interested in, right? And so in this case, it's going to be the proportion of sampled Americans who have good intuition about experimental design. And we have our P hat, which is our sample proportion. Okay. Let's make a note here. Doesn't hurt. In this case, P hat is going to be from here. 571 kind of gave the right answer, right? Have good intuition about sampling design or experimental design. So 571 out of 670. This tells me that my number of successes is 571 and my N is 670. Okay. We usually skip writing out X is the number of successes, but it's nice to see it every now and then. Why not? Only because I'm leading into chapter or section 6.2. So then we'll need the X's and be familiar with the X's. Okay. Where X is the number of successes. Okay. So last week we worked up towards, okay, and so what percent of all Americans have good intuition about experimental design? And so we could answer it using a confidence interval, right? We've got our point estimate, which is our P hat in this case, plus minus some margin of error, okay? And we also established that last week, we said, okay, the margin of error is actually just a critical value times the standard error of the point estimate. Now, for us, for a proportion of one sample proportion, right, the general standard error of a proportion is P times 1 minus P over N. But then we had that problem of, okay, well, we don't actually know P. We don't know P. So the standard error for P hat for a confidence interval, it's probably down here, but that's okay, is P hat times 1 minus P hat over N. Right, we just replace those P's with P hats. And I'm specifying that this is for a confidence interval because for a hypothesis test, then we're hypothesizing that the population proportion is some number. So then we use that instead. Yeah. Slightly different, but as long as you're reading your formula sheet carefully, then it's not going to trip you up. Yeah. How do we find let's review the critical value. The critical value is your Z star, which that's where we're going to use the T table, right, as a shortcut. And so you can use, and this week you'll see in Excel how to use Excel in the lab. But we can use the T table as a shortcut for finding these Z stars. So this is all a review from last week. Yeah.
Back up to the previous slide. So if we don't have the P value, we can just use the P hat.
Yeah.
Is there any, is that just a rule or is there a specific?
For confidence intervals, we use P hat. Okay. And for hypothesis testing, we use P naught.
Okay.
Yeah. So it depends on what we're doing. Good. Everyone wants a piece. All right. So we talked about the central limit theorem of proportions, and we said, okay, it follows a normal distribution, approximately normal, with a mean of p and a standard error of this p times 1 minus p over n, and then square rooted, but that's only under certain conditions. Now, I've kind of glossed over the conditions, but we do need to talk about them, and this is the section that we do that. Okay, and so we have to have independent observations. We've said that before. And some of the ways that, let's see here. Yeah, I'll just, independent observations. We can get there through random sampling and just making sure that our N is less than 10% of the population, which is kind of a weird condition. We want it to be big, so our sample size needs to be big, but not too big, because then you lose independence and kind of a fine balance. And then we have to have at least 10 successes and at least 10 failures. Now, in this example, we said we had X was 571 and N minus X, which is the number of failures, right? If you have N, X of them are successes, then N minus X must be failures. Whereas 99 from the table. Both of those are greater than 10, so that condition is satisfied. Yeah. Now, we're going to do check the conditions here, so that's why I'm skipping through it. So the GSS found that 571 out of 670, or we could have said 85% of Americans, right? But we don't usually give all three, right? We either give the proportion and the sample size, or we give the number of successes in the sample size, and that's all you need to solve these problems. Yeah. So 85% of Americans answered the question on experimental design correctly. Estimate, using a 95% confidence interval, the proportion of all Americans who have good intuition about experimental design. Okay. Now, usually I would write this out, and I'm, again, resisting the urge because they're going to hold our hand through it in the slides. So, like I said, first thing you want to do is just outline the information that you've been given. In this case, we're going to focus on the p hat, which is 0.85, which is 571 out of 670, right? So you could have done it that way. But first thing we're going to do is check the conditions. Now, this is, we have ignored this before earlier, because there was so much to introduce, right? Checking the conditions is one of those things that really throws people off, because you want to tell me, oh, this isn't satisfied. Well, that's not true. It's always going to work out. You just have to argue that these conditions are met, because otherwise you can't answer the problem. So it's one of those things that we force it through. We say, yes, we can assume independence. Why? Well, I can assume independence because the sample was randomly sampled. Even if it doesn't say, I assume it was randomly sampled. Okay. 670 is less than 10% of all Americans, right? If you had more than 10% of all Americans, what would happen is your sample would be too large, and all of a sudden there would be non-independent observations. So that's the concern. But honestly, you're never going to have this problem, right? This is always going to be satisfied that you have less than 10% of the population. Okay. So therefore, we can assume that one respondent's response is independent of another. So that's one of the conditions that we need to check. Okay. On the test and the final exam, I need to know that you know the conditions, right? So telling me independence and then saying something like random check is good enough in my books, okay? So it's gonna look something, this is the cheater version. Can't tell anyone I'm letting you off the hook like this. But so for example, you might say something like this. What you need to say is that independence randomly sampled. Yep, moving on. And the success failure condition, that's where we need a little bit more work. I have the number of successes, X, so then I'm just gonna use it. Or if you only have p hat, then what would you have to do? You would have to take n times p hat. So n times p hat is equal to x, because p hat was what? P hat was x over n. So you've just moved it over, right? And so, which is 570, which is greater than or equal to 10. Good. You have at least 10 successes. That's good. And you need at least 10 failures, n times q hat, or that's the same as n minus x, depending on what information you have, which was 99, which is also greater than or equal to 10. Okay. So in terms of what I need to see, I'm fine with this. Okay. You can mark this day, November 6th at 11:19. That's when I said it. But you said this was enough. Yeah, I did. Okay, you got me. For a confidence interval. And the reason I'm highlighting that is this is for a confidence interval, because this success failure condition is going to change just slightly for a hypothesis test. Right? And it changes in the same way that the standard error changes. Okay, so you've got a clue on your formula sheet. Okay. So for practice, we want to build a 95% confidence interval from the t-table, or if you just have it memorized, a 95% confidence interval has a critical value, a Z star of 1.960. Where did I get that from? You could use your Z table, but it's way more work. And I don't want to do that. Oh, it's already highlighted. Nice. So here's your t-table. It looks very similar to your Z table, right? Except it's got the confidence level up top, and you've got whatever, you choose whatever confidence level you want, and then you trace down, you ignore everything until chapter 7, and then you have Z star down here at the bottom, and it tells you 1.960. Okay. And I'll only ever ask you for these confidence levels. You could, if you had Excel, you could find any confidence level. Okay. And using the Z table, but it's super annoying. So this is from the T table. So now is a good time to ask again, does anyone need a T table? Uh-oh, seems like it's handy. It's up here. All right. So for a 95% confidence interval, right away, we know that, okay, this critical value, right, has to be 1.96, which means that D is out. Okay. What's the next thing? Our point estimate is P hat. P hat was 0.85. So right away, I can't have D. So I'm choosing between A and C, I guess. All right, what's the difference between the two? It looks like, so 0.85, they've got the same point estimate, they've got the same critical value, but different standard errors, right? And this one just looks terrible. I don't like it. but let's just confirm. So I've got p hat 0.85 times 1 minus p hat 0.15 divided by n 670, then square rooted. This is the one I want, right? Not this one, because it only square rooted the n, and that's, I don't know where they got that from, but we've got our winner, which is also on the next slide, I think. Whee! They did the math. They did the work. From 0.85, we can go down a little bit, the margin of error, which we can calculate 1.96 times the square root of 0.85 times 0.15 over 670. Whoo! And then we go up that amount, right? And so then we get this confidence interval. We have to interpret the interval. Because I've promised that that's always going to be half the marks for a confidence interval, right? The math for a confidence interval is not hard. It's the interpretation that can be a little bit sneaky. Now you're going to use my pre-baked interpretation until you're ready to fly on your own, which I'm totally fine with being never. Keep you in my, I don't know, my nest. We are 95% confident, right? Because we built a 95% confidence interval. 95% confident, the interval from 0.82 to 0.88, and then that keyword captures. What are we trying to capture? The population proportion of Americans who have good intuition about experimental design. Captures. But after captures, you just reword the question as an answer, right? That's all I did. It's a lot of words, but you just reword it as an answer. Captures the population proportion of Americans who have good intuition about experimental design. Nice. Now let me just, the margin of error here is what, 0.03? It looks like. I'll do approximately. Where did I get that from? To get from 0.85 down to 0.82, I had to move down 0.03, and from 0.85 to 0.88, I had to go up 0.03. So it's a rough, the margin of error is roughly 0.03. One of the things that we might want to do, that happens quite a bit, is what if I wanted to change that margin of error, right? What if I'm about to conduct this survey again the following year, for example, and now what if I want to tighten up this interval, right? What if I want to make the margin of error be 1%, right? This was a margin of error of 3%. What if I want to cut it down? We know from the way the formula is laid out, right, I would need to increase my sample size. And so this becomes a sample size calculation. So if we have to, so how many people should you sample in order to cut the margin of error of a 95% confidence interval down to 1%? Okay. So if we go back to our roots here, p hat plus minus the margin of error. The margin of error is Z star times the square root of p hat. No, I'm gonna go q hat because I'm lazy. Q hat over n. Huh? Knowing that we're going to be reporting a 95% confidence interval forces Z star to be 1.96. So that's good. All right, that's one thing down. So now we want to solve for n. Solve for n, that makes the margin of error be 0.01, right? Usually what's happening though is, so this is a sample size calculation. Okay? Often what's happening is I don't have a p-hat. This is before I've conducted any studies. Okay, so what we're going to have is we're going to replace, now let's see here. Can I do this? So many arrows everywhere. We often do not have a previous study. So we won't have p-hat. That's a problem, right? P-hat is a sample proportion, and if you have a previous study, then that's what you would use. Okay? But what can we do? P-hat is a proportion, okay? And if you go through and you multiply, for example, 0.6 and 0.4, 0.2 and 0.8, for example, what you're going to find is the largest possible value that you could get is when you have 0.5 and 0.5. You just assume a 50-50 split. Okay? And so in that case, use, and I'm going to call it P star equal to 0.5. So now generically, I'm just going to call this P star because it can take the form of two different things, right? If you have a previous study, then you use that as your P star, your P hat, or if you don't, then you use a 50-50 split. Okay? And when I worked at the market research firm, did a lot of social surveys and stuff like that, and they'd always come and ask me, hey, what sample size do we need to calculate? And I'm like, oh yeah, sure, we can do that. I was doing this a lot. It's not terrible. But then one day they brought out this, they had this wheel where you adjust the confidence level and the margin of error, and then it gives you an output. And then I showed them the math is not really that hard. So I think they kept the wheel though. They liked it. But it's not hard. What would you have to do here? If I say, okay, the margin of error, let the margin of error be denoted by a lowercase m, right? Because otherwise I have two things and it looks bad. Then m, oops, that doesn't look like an m, is Z star. And I'm going to replace it with a P star Q star, where Q star is, of course, just 1 minus P star divided by n. If I want to solve for m, and don't worry, we're just going to derive this, but the formula is on your formula sheet. What? Where? Aha, I'm withholding for a little bit longer. But I'm going to add a page. Oh, and I need some lines on here. Hey, it added it in the wrong spot. Let me, okay, that's better. So now I've got this little guy, I'll put it on a fresh page here. And we want to solve for n. first thing you'd have to do is divide both sides by Z. So M over Z star is the, you know what? Just gonna scoot it over a little bit so it doesn't look so weird. Is the square root of P star Q star over N. Trying to get at that N, I'm gonna take the square of both sides. So I have M over Z star squared is P star Q star over N. Trying to solve for N, I'm gonna move this N over to the left. So then I have N times M over Z star squared is P star Q star. Good. If I'm dividing a fraction, right, I can rewrite P star Q star as a fraction over 1, right? So then I would have a fraction over a fraction, but what happens is I have to flip the denominator and multiply, and the square goes with it, and we get to N is, writing it as it is on your formula sheet, Z star over M squared P star Q star. And now I'll bring in from your formula sheet. Right, from your formula sheet. So it's there, you don't have to do the derivation, but it's just nice to see where it came from. Okay, where P star is going to be 0.5 if no previous studies exist. If no previous studies exist, or P star is P hat from a previous study. What happens when we use the 0.5 is it's going to give us the largest possible value of N that you could need, which means it's more expensive than, so if you have some prior knowledge that would let you cut down on the costs a little bit because the value of N that you would need is just slightly smaller, right? Then you would want to do that. But in general, you're always safe to use 0.5. It's just going to give you the most conservative value for N. Now, one of the things when you solve for N is you're always going to round up, right? So even if you get a value of 42.01, you have to sample 43 people, right? Otherwise, your margin of error would just be slightly bigger than what you wanted, and that's bad. And why not just sample one more person? And so once you have calculated N, you must round up regardless of the decimal. And I'm not going to write it there because that's just a rule for you to remember. But the reason would be that the margin of error would be just slightly bigger than what you wanted. So mission not accomplished, right? And so, for example, if you find that N is 42.01, just to use that example, right? We would need to sample 43 people, right, to meet that criteria. Feels weird, yes. And does it matter? No. but it's just one of those things. Yeah. Okay. So here they do it, but we already did it. So we'll kind of zip through here, but we didn't do it with any values, right? We just talked about it in general, okay? And so what we want is we're gonna force it to be a 95% confidence interval, and then I'm gonna make it equal to 0.01, right? I'm gonna force the margin of error to be 0.01. They're getting super fancy with the greater than or equal to, okay? It's weird. But then, okay, they do the derivation, but I kind of did it in a different order. That's okay. You can just use the formula on the formula sheet, right? So here, from the formula sheet, n is z star over m squared, and then p star q star. This is using p hat as your p star, right? Because we have that previous study. And so here we've got this note of 4898.04, but we would need 4899 in order to satisfy the criteria. Good. Like we said, what if there isn't a previous study? Then you're going to use 0.5. Okay. If you don't know any better, so some of the reasons, if you don't know any better, 50-50 is a good guess. Right? Why not? And it gives the most conservative estimate, which is the highest possible sample size. Okay. And let's just quickly do it. N is z star over m squared times p star q star. In this case, 1.96 over 0.01 squared times 0.5 times 0.5. I'm just doing it real quick because what I want to do is just compare the values of n and see how they change. 1.96 divided by 0.01, gonna square that, times 0.5 times 0.5. I get a nice even 9,604. Right? I don't need to round that because it's already done. But if I compare that n to 4,899, which one would you rather pay for? 4,899 people sampled or 9,604 people sampled? Let's say you're giving out $10 gift cards, which isn't very much if you're on the survey taking side, right? But if you're trying to get these completions, right, please do our survey. We'll give you a $10 gift card, please. That cost is quite a bit more, right? And so that's the difference between, right? The only thing that changed is what p star we use, right? So this is why it's the more conservative estimate, but this is the largest possible value of n that you could need for a margin of error to be 0.01 at a 95% confidence level. Ugh. Okay. Good. Sample size calculations. Okay. So the conditions, this is referring to the conditions. So going back to the conditions for conducting a confidence interval or doing a hypothesis test. Now, we did the work and we figured out, okay, how do I make a confidence interval? How do I interpret it? How do I do a hypothesis test, right? How do I draw my conclusion? But before we did all those things, we should have been checking the conditions. But like I said, they're always going to check out. So I like to skip ahead and then go back and reintroduce it and be proper. So for the success failure condition, which means that the independence condition is always the same. So independence is randomly sampled and n less than 10% of the population. That's the same for both. But like I said, you can do a cheater version and just say random check. Unless it doesn't say that it was randomly selected, then you would have to say what? I assume the sample was randomly selected. So either way, you're going to say random check. Now the success failure condition changes just ever so slightly depending on if you're doing a confidence interval or a hypothesis test. Okay. So for a confidence interval, we need at least 10 observed successes and failures, right? So we've got, right, x greater than or equal to 10 and n minus x greater than or equal to 10. Or how else could we write it if we have our p hats? We could have n times p hat greater than or equal to 10 and n times q hat has to be greater than or equal to 10. For a hypothesis test, what we're going to check is that we have at least 10 expected successes and failures calculated using the null value. Okay. So what we're going to do, and the reason I wrote this out is because they're very similar, just with a very slight tweak, is that we're going to do n times p naught has to be greater than or equal to 10, and n times q naught has to be greater than or equal to 10. From the null hypothesis that p is equal to p naught. Okay. So just very, very slight change. Okay. From the formula sheet, hey, it's missing hats, which is important. Big time error. The standard error calculation is going to kind of guide you to how do you check your success failure condition, right? Because here, the standard error from the confidence interval, which is on your formula sheet, right? It has the square root of p hat times 1 minus p hat over n. And so for a confidence interval, you're going to check that n times p hat is greater than or equal to 10 and n times q hat is greater than or equal to 10, right? And that's why those p hats are so important, right? So you use that to check your conditions. Whereas for a hypothesis test, right, we use p naught in our standard error calculation because it's our better guess at what the population might be, right? So then for the success failure condition, you're going to do NP naught greater than or equal to 10 and NQ naught greater than or equal to 10. So let the formula sheet be your guide. You can usually bank on me being pretty tired when I'm marking, or just as soon as I start, I'm like, oh, I don't want to do this. Get into all your brains and figure out what you were thinking in that moment. It's exhausting. So then usually, now you can't quote me on this because I might be really mean. If you just write success failure condition check, that's like half a mark. Just, you knew that you had to check it, you just blanked on how to do it. That's worth something. So you can usually bank on that, right? Independence, random, check. Success failure, check. Like, yeah, okay. I could go for that. Usually I write okay if it's something that I'm not 100% with, but it's okay. All right. So how about a hypothesis test? So we can use the same information to do a hypothesis test. Now, what we want to do here is, do these data provide convincing evidence? And that's the word of the day, evidence. As soon as you see evidence, you're going to think, oh no, it's a full-blown hypothesis test. Do these data provide convincing evidence that more than 80% of Americans have good intuition about experimental design? There's an A in there, but I can't decide. Cut the A, keep the A. Doesn't matter. We're gonna do the hypothesis test. All right. So first thing we want to do is we're going to check the conditions. Now, I'm pretty sure. Okay. We'll do it together. Let's check the conditions. What were the conditions? Independence. Was the sample randomly sampled? I think so. Randomly sampled. Check. Huh? Is it bad that I'm cutting corners to show you where you can cut corners? I think so. 670 is less than, so this is the N less than 10% condition. 670 is less than 10% of all Americans. American adults, presumably, but whatever. So we already established that we're going to have to do a hypothesis test. Okay. And so that changes the success failure condition. Oops. Which sometimes we call the normality condition, but I don't want to bog you down. But if you see kind of old solutions or whatever, it might call it the normality condition, which it is. Otherwise, it doesn't follow a normal distribution. Which is something we're assuming when we use the Z-score calculation in our test. Oh, they're all hand in hand, aren't they? N times P naught. I have N. N is 670. P naught. This is one of those scenarios where you kind of have to have an idea of what your null hypothesis is, or at least your P naught value, right? P naught is the value you want to compare your sample proportion to, right? So you're going to have a sample proportion 0.85, and you want to know, how does it compare to 0.8, right? Is it significantly more than 0.8 is what we want to know. So your P naught here is 0.8. Yeah. And if you find it more helpful to set up your null and alternative hypotheses before checking the conditions, that's totally fine. But I like to do it first. Times 0.8. 670 times 0.8 is 536. So that's my expected number of successes if the population proportion was 0.8. Okay. Which is, of course, greater than or equal to 10. Good. N times Q naught. You could take 670 minus 536, or just 670 times 0.20. Either way, the math's not coming. 670 minus that, 134, which is also greater than or equal to 10. Okay. I can't stress this enough. The conditions are either you have to assume that they're met, or they're just always going to be satisfied. Okay. I see too often on a test, you're trying to get it all out there, and then you want to tell me that the conditions are not satisfied. Are you allowed to do the hypothesis test if they're not? No. So then if you continue, I'll ignore it, obviously, that you told me that you couldn't. But in real life, that would be really bad, right? Well, we can't do that, but here, yeah, I'm just going to do it anyways. So don't do that. It will always be satisfied. You just have to show it. Okay. Or in the case of the randomly sampled, argue it, right? Even if it doesn't say that it was randomly sampled, you could say, I assume it was randomly sampled. It's fair. Okay. Now I think we're ready for the next slide. First, from this little blurb, let's just do a quick check-in on what we think the null and alternative hypotheses might be. So H naught from your formula sheet is P is equal to P naught. You've established, or you would have established, we've only seen one type of question so far, so it's hard to compare the two. But we have one sample of 670, and I have a proportion that I'm interested in. So it's a one sample proportion question, which targets that area on your formula sheet, right? And you just ignore the rest. Nothing else is there. Which means it also tells you that the null hypothesis is that P is equal to P naught. Your job is to fill in and figure out what that P naught is, which we already did. So then your null hypothesis is that P is equal to 0.80. What do we actually want to show, right? We're hoping to be able to show that the alternative P is more than 0.80. Which means I have a one-sided test, right? In fact, I'm only going to be concerned with the upper tail in my p-value way down later in step 3. Okay. But here I make a note that this is a one-sided test, which means I'm going to have a one-sided p-value. Okay, that's hard. Arguably the hardest part of doing this, besides it just being a new procedure. But once you've got this all done, then what's your next step? Is doing the find the test, or do the test, calculate the test statistic if you're boring. So we've got our null hypothesis is that P is 0.8, and our alternative is that P is greater than 0.8. We do all our testing assuming that P is 0.8. Until we find evidence that actually 0.85 was quite a bit higher than 0.8 once we took into account the standard error, right? And so that gives us evidence to say that this is unlikely and this is more likely to be true, right? And so that's the general idea of hypothesis testing. We have to calculate the standard error. I usually just do it in my Z. Z is P hat minus P naught over the square root of P naught Q naught over N, which is the standard error. That's on your formula sheet. What does that Z tell us? Z tells us how far P hat is from P naught in terms of the number of standard errors, right? And so P hat is 3.25 standard errors above P naught, which is really far, right? We use 2 as kind of a guide. Anything beyond 2 standard errors is going to be too far away to be considered the same, right? And so what do? This is kind of breaking it down. This is step 1. This is step 2. Here. And then the p-value, I call it step 3. you're more than welcome to just smush it all up, but I like to break it down and just focus on one part at a time. This was, of course, a series of slides that built up to this, but I just skip right to the last one and I delete all the other ones. I don't like it. The p-value, to figure out which area you want, right? Remember, the p-value is the probability of seeing something as extreme or more extreme than what you saw, assuming the null hypothesis is true. So we had a 0.85, which we know is 3.25 standard errors above 0.8. Okay? So we already know that it's really far away. Okay? And so what do we need? The probability of seeing something as extreme or more extreme would be the area in the upper tail. Okay? This also maps back to, and I guess I don't need to write it out because it's all on the same slide. This maps back to this alternative hypothesis. If you've got a greater than here, then you're only interested in the upper tail, right? If you had a not equal to here, you would find the area in one of the tails and replicate it down in the other tail because you're just as concerned about that other tail as you were with the one that you saw. Okay. So from the Z table, you can find that, okay, we've got a Z of 3.25. So if I go to my Z table, which is where? Gone forever. 3.2, I'll highlight that row. 3.25, it's been a while, right? Since we were here. But we get an area to the left of 0.9994, which means that the area to the right, which is the one that we want, is 0.0006. That's what we use. That p-value is what we use. We could have used the z-score, but it's really hard to communicate to your boss, for example. Well, because it was 3.2 standard errors away from the hypothesized value, that's why we rejected it. It's a no thank you, try again. Because the probability of seeing a sample proportion of 0.85 when the proportion is actually 0.8 is as small as 0.0006. That's a reason that I'm going to reject the null hypothesis and say in favor of the alternative hypothesis, right? That gives me evidence to say that unlikely, right? It's more likely that p is actually greater than 0.8. Okay? And so there's this probability that we're wrong, 0.0006, but we're okay with that. In fact, we're okay with being wrong 5% of the time, right? And so we set the, how do we determine if it's low? We compare it to an alpha level, right? So here we've got an alpha of 0.05. So once we pass this threshold and we say, well, the probability is less than 5%, that's a reason I'm going to reject the null hypothesis, right? And so here we have, since the p-value is low, which really what we're saying is less than alpha equal to 0.05, which is our default, the significance level. We need some threshold for the p-value to be too small, right? Because if the p-value is low, then you can reject the null hypothesis, right? If the p is low, then the null hypothesis must go. It's got that ring to it. Or you can ask Snoop. Either way, it's all the same, right? And so if we reject the null hypothesis, what does that mean? It means that the data provide convincing evidence that more than 80% of Americans have, I still am unsure about this A, have good intuition on experimental design. But that's just rewording the question as an answer, right? Which is arguably the most important part, right? And so, do these data provide convincing evidence that more than 80% of Americans have good intuition about experimental design? Yes. The data provide convincing evidence that more than 80% of Americans have good intuition on experimental design, right? You either they do or they don't, depending on what you found in your test. Now, one of the things that I don't do, but you could do, instead of the p-value, right? Instead of finding this probability, you could say, well, what z, right? What z makes 0.05 in the tail, so 95% below it, not central, okay? You could find a z value that makes that happen, and then you could compare your z's. I don't like to do it that way, but you can play around with that and say, well, my z of 3.25 was bigger than this critical value, which is what we call it confusingly, right? Not a z star, but a critical value. So either way, you've got this visual of your observed p hat moved past this boundary, right? And therefore the area in the tail is less than the 0.05, or you could translate this to being a z of 3.25 past a z of 2, for example, right? I don't know what the exact value is. Okay, fine, let's find it. What am I gonna do? I'm gonna sneak attack it a little bit, and I'm gonna apply the symmetry, and I'm just gonna find the table entry closest to 0.05. 0.05 looks like, oh, I had it and I lost it somewhere here. Negative 1.645. I'm gonna go for the midpoint. And I know that's rude, but it's not something that I expect you to do. But that was on the lower end, and I'm using symmetry to put it in the upper end, so then it's positive 1.645. How do I know it's 1.645? I could have also used the t-table. 90% confidence interval has 10% in the tails, but I only want 5% in the tails, so it's kind of in a roundabout way. So then what you could say is that here, this z of 3.25 is larger than 1.645. Therefore, I have enough evidence to reject H naught, right? Because this is more in the tail than 1.645. That's another way that you could do it, and you're welcome to do it that way. I will understand what you mean, but I like to just use the p-value approach, and then as you kind of grow your hypothesis testing muscles, then maybe you'll head in this direction, and maybe you like this better, right? But for me, I like to just stick with one approach. I introduce it like this, but so you know that you could if you wanted to. That's totally fine, but it's enough of that. Or is it? And what time? Okay, we're still good. How about a different example? 11% of 1,001 Americans responding to a 2006 Gallup survey stated that they have objections to celebrating Halloween. Hey, we should have done this just a smidge earlier. So close. To celebrating Halloween on religious grounds. At a 95% confidence interval, the margin of error for this survey is 3%. Okay. So 11% plus minus 3%. So now we have a confidence interval if we wanted it. A news piece on this study's finding states more than 10% of all Americans have objections on religious grounds to celebrating Halloween. At the 95% confidence level, is this statement justified? Yeah. So what we have is, okay, we have the 11%, which is more than 10%, right? Which is where this more than 10% came from, right? But we also know that this is just a sample and there's variability around it. And so we're gonna go down to 11 minus 3, which is 9, 8. You win some, you lose some, right? $11 plus 3, 13. Wait, I have to be careful that I don't write the wrong thing. There. Okay, and so this is our confidence interval. So now, I almost threw myself for a loop. So now, right, the more than 10%, well, 10% is here, right? And we're 95% confident that somewhere between 8 and 14%, right, have objections, blah, 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 which is not all more than 10%, right? And so, no. Since the interval goes below 10%, and maybe I'll clean this up. No, since the interval goes below 10%, right? In order for, yeah.
Would it be true if it was 14 plus or minus 3%? Like if the interval stayed above 10%?
Yeah, totally. So even if it was plus minus 0.05, right? I'm just trying to get it so it's all above 10, right? Then, right, if we let the margin of error be 0.05, right, then I would be going from, let's see here, 10.5 to 11.5, which is all above 10%. Therefore, it would be justified. But in this case, right, 10 is in there. In fact, it can go below 10 down to 8, and we don't know or care. And so that's why it's not justified. We saw this, or did we? Now I can't really remember. This is a way of doing a hypothesis test with a confidence interval. Have we done that yet? Searching your faces.
You briefly talked about it.
Just so briefly, huh? Okay. We can. What's this doing? This is testing the hypothesis that P is 0.1. But the alternative, what they're trying to claim is that P is greater than 0.1. Right? We can use a confidence interval as kind of an informal hypothesis test instead of calculating the test statistic. And instead of calculating the p-value, you can look at the interval and say, well, I'm 95% confident that it's somewhere between here and here. And if the hypothesized value is inside the interval, right? If P equal to 0.10 is within the confidence interval, we do not have enough evidence to reject H naught. But on the flip side, if it's outside the interval, right, assuming it's on the correct side, right, if it's greater than 0.1, then obviously the interval has to be all above 0.1. If it's less than 0.1, the interval has to be all below 0.1. If it's not equal to, as long as the hypothesized value is not in the interval, then you can reject H naught. So if P equal to 0.1 is not within the interval, we have enough evidence to reject H naught. There's a tiny caveat, because a confidence interval is technically only for a two-sided test, right? Because you've gone from the center, you've moved out in either direction. So now you have area in both of the tails. So it's technically only supposed to be applied for a two-sided test, which would be P is not equal to 0.1, right? Which is just a general version of P being greater than 0.1 or less than 0.1. So technically, that's the caveat, but I'm choosing to ignore it for now or forever till a later course in statistics. How about that? But now you've heard it, and then next time you hear it, you're gonna say, ah, she was blabbing about something like that. Ah. Lost it now. Okay. Just hyper aware of, I thought you'd put your hand. Swing around. Okay, so just a little recap. Inference for one proportion. This is our first type of question. So one sample proportion. I like to emphasize one sample proportion. That's our first type of question done. Okay. And so for one sample proportion questions, first off, the parameter that we're trying to estimate is P, right? The population proportion. Our point estimate is P hat. Sample proportion, good. The conditions are going to be independence is that it's random, and the less than 10% of the population condition. It's okay if you forget that one because it's never going to be an issue. Unless you're crazy rich and all you want to do is collect samples, then you need to rein it in, but that never happens. And then at least 10 successes and failures, which leads down here. You use your standard error as the clue. And so for confidence intervals, you use P hat, and for hypothesis testing, you use P naught in your standard error. Okay. So here, this is, oh, it's not what I meant to do, but it's pretty cute. Okay, that doesn't look like an arrow, does it? There. Hey, it looks like it has sunglasses on. Cool. It's a cool arrow. Conditions. You check them, you move on. Whoa. It's a recap of the conditions. I guess we just did examples of confidence intervals, hypothesis testing, but what I want to do is I want to insert from the formula sheet all the things that we could do, the places we could go. I was hoping it would just show up through, but there. So then here, one sample proportion puts you in the one sample proportion section of your formula sheet. So the first thing you're going to do, obviously, is identify what type of question you have. Okay. And this is just here for show, but it's also highlighting what your standard error is, right? And then for a confidence interval for P, you've got your point estimate plus minus some critical value times the standard error of that point estimate, which uses P hat, which is your clue to use P hat to check your conditions. Hypothesis testing for P You've got your null hypothesis is P is equal to P naught. It's your job to find P naught from the question. What's the thing I want to compare my sample proportion to? Okay. And then you can use that from P hat minus P naught. How far away are they from each other? Taking into account the standard error, which is now using P naught, which is your clue to use P naught to check your conditions. Your Z tells you how far away they are. You translate that into a probability because it's easier to communicate. That's your p-value. And then if the p is less than the alpha level, then you have enough evidence to reject H naught. So if the p is small enough in favor of HA, or vice versa. Or we can calculate a sample size given some desired margin of error and potentially some past sample proportion, or if you don't have that, you use 0.5. And bada bing, bada boom. On Wednesday, we're ready for our second type, which is 2 proportions, so 2 sample proportions, but I'll hold off till then. If you have any questions, let me know. Otherwise, I'll see you on Wednesday. And I'll stop this.